Okay, great. So it's a great pleasure to have you all back at our weekly seminar. And today we will have Istvan Tomon from Umea University, and he will tell us about Zarankiewicz problem for various hereditary families. Yes, Istvan, please.
Thank you, Benny, and thanks everyone for joining. So one of the most notorious open problems in extremal combinatorics is Zarankiewicz problem, which in its simplest formulation asks for the maximum number of any edges in an n-vertex graph which does not contain the complete bipartite graph KTT. So I say that this is the simplest formulation because in the most general formulation we are looking at bipartite graphs which do not necessarily have equal sized vertex classes, and we are asking how many edges can we have in such a bipartite graph without a copy of KST, so not necessarily balanced complete bipartite graph. However, in this talk, I will concentrate on this simple formulation to make our life simpler. So for this question, one of the fundamental theorems in the area is the Kőváry-Schuh-Stüren theorem, which gives the upper bound constant times n to the 2 minus 1 over t. So this bound is only known to be sharp for t equals 2 and 3, but it has not been improved in the past 70 years, and it is widely believed that this should be the right answer. However, in general, the best known lower bound, which can be easily proved from essentially the probabilistic deletion method, gives n to the 2 minus 2 over 2 plus 1. So while there is still some gap between the lower and upper bound, we do get this somewhat satisfying answer that the growth rate of this function is n to the 2 minus constant over t. Okay. However, now what we will concentrate on this talk is what happens with this question if instead of looking at the maximum across all graphs on vertices, we focus on our attention with certain special graph families, and we ask that in these special graph families, which graphs maximize the number of edges if they avoid KTT. So this problem can be formulated as follows. So let's say that we have a family of graph F, and let's assume that it's hereditary, which means that it's closed under taking into subgraphs. And then we ask that how many edges can an unvertex member of F have if it contains no copy of the complete graph KTT, complete bipartite graph KTT. And let me denote this maximum by Z, F, and T. So this question has been extensively studied in the past 2 decades, and there is a lot of motivation coming for these kind of questions from both structural graph theory and also combinatorial geometry. So especially in the past decades, there were some connections discovered with this problem and certain incidence bounds. And so this is something I will talk about later. But then this inspired the kind of systematic study of this function. And the past couple of years, there was a culmination of a number of results which show the following very nice general result about this function Z, F, and T. So you can see this bunch of authors for whose this theorem is attributed. But so basically, there is this theorem which was not really ever explicitly stated, but can be read out from all these works. And what this theorem says that under some very mild conditions on this hereditary family F, the behavior of the function Z, F, and T completely changes compared to the traditional Zarankiewicz number. So what this theorem says that if F is a hereditary family of graphs and it avoids at least one bipartite graph, then we can immediately conclude that there is a positive constant C depending on the family, such that the the order of magnitude of this z f n t is at most some constant times n to the 2 minus c. And yeah, maybe I forgot to mention, but so in this talk we will view the parameter t as a constant which might grow, but we will always view it as independent of n. And so in this case, we get this kind of very different behavior compared to Zarankiewicz. So just to recall, so in the case of Zarankiewicz, we had this exponent tending to 2 as t grew, but here we have this exponent strictly bounded away from 2. And this theorem is also an if and only if statement. So of course, if your family contains all bipartite graphs, then you cannot do really better than just the traditional Zarankiewicz function. And the reason is that the lower bound in the Zarankiewicz problem can be realized with bipartite graphs as well. But now, having this theorem, the big question is that what can we say about this constant c and how does it depend on the family? So unfortunately, we don't really even have a good guess what this constant should be, depending on the family. But we have some nice conjectures, at least in the case when f is defined by a single forbidden bipartite graph. And in this case, we conjecture that the Zarankiewicz function has to be closely related to the extremal function of this forbidden bipartite graph. So what is the extremal number of a graph? So this is another widely studied parameter in extremal combinatorics. So the extremal number of a graph H is just the maximum number of edges in an vertex graph, which does not contain H as a subgraph, so not necessarily induced, just H as any subgraph. So there is a very simple relation between the extremal number and the Zarankiewicz function. So if f is the family of all induced H-free graphs and t is sufficiently large, so let's say t is at least H, then the Zarankiewicz function z f n t is at least as large as the extremal number of H. So why is this true? So if we have an H-free graph, so if we have a graph which does not contain H, then of course it does not contain H as an induced subgraph either. And also if t is greater than H, then KTT contains H as just a normal subgraph. So we cannot have KTT either in a graph which avoids H just as a subgraph. So this shows this lower bound. And now we propose this kind of brave conjecture that actually these two functions should be equal up to constant factors. So we propose this conjecture that if H is bipartite, T is sufficiently large, and F is the family of all induced H-free graphs, then the Zarankiewicz function is asymptotically equal to the extremal number of H. So now so this conjecture is still mostly wide open, and one difficulty with this problem is that we already don't really understand the extremal numbers of bipartite graphs. So it is a major open problem to determine the extremal number of bipartite graphs, and there isn't even a reasonable conjecture what this should be for a generic bipartite graph H. However, we can still show some kind of evidence for this conjecture, because there are certain families of bipartite graphs where we have a good guess what this exponent should be. And for many of these graph classes, we can show that the Zarankiewicz function behaves very similarly. So to give you a few examples, so one celebrated result in the area is first proved by Furedi in the 90s, and then later proved by Aleksa and Sudakov using the dependent random choice method, says that if we are looking at bipartite graphs where in every vertex in one of the vertex classes have degree at most d, then the extremal number of this H is at most constant times n to the 2 minus 1 over d. So here we are looking at the graphs H, where in one of the parts, let's say in the upper part, every degree is at most d. So, now for these graphs, we have this extremal number, and actually we know that there are graphs H of this form which achieve this bound, so this cannot be improved without further assumptions. Okay. And one of our main results shows that we can reproduce the exact same behavior for the Zarankiewicz function. So again, if H is a bipartite graph which satisfies this maximum degree condition on one of the parts, and F is the family of all graphs which avoid H as an induced subgraph, then the Zarankiewicz function is exactly the same, some constant times n to the 2 minus 1 over d. So another well-known result in the extremal graph theory of bipartite graphs is the Bondi-Shimonovich theorem, which gives an upper bound on the extremal number of even cycles. So we know that odd cycles are not bipartite, so their extremal numbers are quadratic. However, for even cycles, we have the Bondi-Shimonovich theorem, which gives that x and c2k is at most constant times n to the 1 plus 1 over k. So again, this, while we don't know whether this bound is sharp, so this bound is only known to be sharp when k is 2, 3, or 5, there is this kind of general belief that maybe this is the right answer. So I'm not sure how strong this belief is. But anyway, so for again these cycles, we can recover the same bound for the Zarankiewicz function as well. So we show that if we look at the family of C2K3 and KTT3 and vertex graphs, then the number of edges goes at most constant times n to the 1 plus 1 over k. And so there are other few examples where we can show a similar behavior, but instead of walking you through all these examples, let me show you another nice problem about the Zarankiewicz functions, and that is to try to determine that for which family is F, so for which hereditary family is F, is it true that this Zarankiewicz function grows linearly none? So these graphs these families even have their own name. They are called degree bounded families. So again, so a family is degree bounded if z f and t is at most constant t. And why we're interested in these families is that it turns out there is an abundance of very natural such families, both in structural graph theory and combinatorial geometry. So to give you a few examples of degree bounded families, so one can show that the family of graphs avoiding for ST as an induced subgraph, they have this degree boundedness property. And note that this is also aligned with our conjecture because it's very easy to show that the extremal number of forests is linear. So we had the matching Zarankiewicz function as well. And another, so this is kind of one of the first results in this area is a result of Kunanostus, which shows that the family of graphs avoiding all induced subdivisions of the complete graph, or basically any graph, is degree bounded. So here to give you a picture, so the subdivision of a graph is just we take any edge, and we replace with a path of any length. So that's called a subdivision. And now in this case, we are not only forbidding one subdivision, but we are forbidding also subdivisions. So now we are forbidding an infinite family of graphs. And for these families, you can show that they are also degree bounded. Another, here is a geometric example of degree bounded families. So one celebrated example is due to Fox and Puck, who showed that so-called intersection graphs of curves, also known as string graphs, are degree bounded. So then a string graphs, just to give you a picture, so curve is just basically anything you can draw on the plane without lifting your pen, so just the image of any continuous function. And if you have a bunch of these curves on the plane, some of them intersect, some of them not, but you can assign a graph called intersection graph where you view these curves as your vertices and you connect two by an edge if they have a non-empty intersection. So for these two curves, so this curve is joined to this curve, and this curve is joined to this curve, and so on. So this defines a very natural geometric graph, and you can show with a combination of geometric and combinatorial techniques that these graphs are also degree bounded. And maybe a final example is an incidence graph of points and half spaces in R3. So then you can have some collection of half spaces and some collection of points. And then you can define the incidence graph where you connect a point by a half space if the point is contained in the half space. Again, these are some very geometric graphs, and you can show that these are degree bounded. Now, interestingly, it turns out that if you go just one dimension up, so you look at points and half spaces in R4, then those graphs are not necessarily degree bounded anymore. Okay. And about having these many examples of degree bounded families led to the systematic study of these families, and so there were several questions that what can we say about these families just by knowing that they are degree bounded. And here there is this beautiful recent result of Girai and Hunter, which says that in order to show that a family is degree bounded, you actually only need to consider the C4 free members of this family. So if you show that the ZFN2 function, so when t is equal to, this grows linearly, then it already implies that this function grows linearly for every t. And not only that, but also if you know that it grows linearly, and you're interested in what is the dependence of t, you can show that it grows at most polynomially as a function of t. And this is the best you can achieve. So just from this very small information of looking at C4 free graphs, subgraphs, you can already deduce a lot of strong things about this family. Okay. And so now let me talk a bit about how this Zarankiewicz problem and how this degree boundedness and how these kind of KTT-free configurations appear in geometry. So let me try to give you even more motivation why we are interested in these kind of problems. So in order to talk about these results, I have to first talk a bit about the VC dimension of set systems. So if you don't know what the VC dimension is, this will be a bit of a rushed introduction. So sorry for that, but basically a VC dimension is kind of a complexity measure of set systems that has a wide range of applications, not only in geometry, but also in computer science and learning theory. So it can be defined simply as follows. So the VC dimension of a set system is just the maximum D such that our set system shatters set of size D, where shattering means that if we take our set system and we project it to this D element set, then this projection witnesses all possible subsets of this set that we projected into. And so the maximal size of set where we get this complete intersection pattern is the VC dimension of a set system. And to give you some examples where this VC dimension appears, for example, one can look at points in the plane, and you can look at the set system generated by say, disks, or let me do rectangles. So you can consider a set system generated by rectangles, which means that you look at all possible subsets of the points you can cut out by rectangles. So this gives you a set system, and you can show that this set system has VC dimension at most 4. So in general, if you replace your rectangles with any nice shape like disks, or in higher dimensions, spheres, boxes, half spaces, basically anything that you can define algebraically, then this set system will have bounded VC dimension, most likely. So this led to just that we want to generally understand how set system of bounded VC dimension can look like. But now we are talking about graphs. So how does VC dimension connect to graphs? So it turns out that there is a very natural generalization of the VC dimension for graphs, where we just denote the VC dimension of a graph as the VC dimension of the set system generated by the neighborhoods. So you have your graph. And then you just look at your vertices. For every vertex, you look at the neighbors. And this gives a set system with n sets. And the VC dimension of the graph is just the VC dimension of the set system. Okay. And then there is this beautiful result of Foxbach, Scheffer, Sukensal from 2017, which shows that if we look at the family of graphs with bounded VC dimensions, so VC dimension is D, then the Zarankiewicz function grows at most as n to the 2 minus 1 over D. And very recently, this was slightly improved by Jansen and Polatas. So we know that actually it grows even slower. So it's at most little o n to the 2 minus 1 over D. However, this bound n to the 2 minus 1 over D has a special significance because there are some natural relaxations of the notion of VC dimension, where you can show that this kind of exponent is actually sharp. And so one way to apply this result is in geometry. So there is this. So let me tell you about this theorem of Foxbach, Scheffer, Sukensal, and recently slightly improved by Tidor and Yu. So they consider geometric graphs which are defined by certain algebraic relations. They show that if we have a graph G, where the vertices can be assigned to points in Rd, and edges are determined by a constant number of polynomial inequalities, each of the constant degree, then assuming this graph is KKT-free, then we have this upper bound that the number of edges is at most constant times n to the 2 minus 2 over D plus 1. So I know that this theorem is a bit of a mouthful, so let me try to give you some more intuition why this theorem is important and how is it used. So one very nice consequence of this theorem is that it immediately implies this Meredith-Trotter theorem, which is a fundamental theorem in combinatorial geometry, which just says that the number of incidences between n points and n lines in R2 is at most n to the 4 over 3. And so what is the relation between these two theorems, and how can we use the theorem upstairs? So let's say we have a bunch of lines and a bunch of points, and we want to count the number of incidences between them. Now what we can do, we can represent both the points and the lines by two-dimensional points. So if I have a point, let's say U and V, and I have a line given by the equation ax plus b equals y, then I can just represent the point uv with itself, while I can represent the line AB, ax plus b equals y, just by the point AB. So now this gives a graph where the points I represented by points in R2. But now notice also that the edges are basically determined by just a simple equality, because we have that the point is contained in the line if and only if AU plus B equals V. So this gives a four variable 2-degree polynomial, and there is an edge between the point and the line if and only if this degree 2 polynomial is satisfied. And in addition, we know that the intersection graphs of the incidence graph for points and lines is K223. Which in case is automatically true because we cannot have two lines which goes through the same 2 points. So we can apply this theorem with t equals 2, and plugging in d equals 3, we get exactly the upper bound constant times n to the 4/3. But now, of course, this theorem has applications that go way beyond that. Now we can look at, for example, the incidences of all kinds of sets of points and algebraic curves. And in many cases, this KTT freeness is somehow an automatic condition. So we don't have to worry about that. And in these cases, we automatically get a very strong bound on the number of incidences between these certain sets of points and algebraic curves. Okay. But so there is one question in this area which I want to go into be a bit deeper. So the Summer-Trotter theorem gives a bound on the number of incidences between points and lines, but there is a very natural question, is that what happens in higher dimensions? So what can we say about the incidences between points and hyperplanes? So this leads to an old problem of Chazal, was that what is the maximum number of incidences between endpoints and hyperplanes in RD, assuming that the incidence graph is KTT-free? So now, unfortunately, when we go to dimension 3, this KTT freeness is already not automatic, because it can happen that I have a bunch of points on a line, and at the same time, I have a bunch of hyperplanes, so just a bunch of planes that contain this line. So in this case, we can have that the incidence graph between the points and planes is a complete bipartite graph, so we need to assume something to avoid this kind of triviality. And so so for this question, Applebaum and Scherrer prove the upper bound n to the 2 minus 2 over d plus 1, which, if you notice, is exactly the same bound as in the upper theorem. And this is not a coincidence, because of course you can represent incidence graphs of points and hyperplanes in RD by d-dimensional points. So this theorem gives an alternative proof of this result. However, it is still open whether this bound is sharp. So currently the best known lower bound in large dimensions is due to Benny Sudakov and myself, where we prove that as d tends to infinity, we get roughly the lower bound n to the 2 minus 4 over d. So there is this factor 2 difference between these two exponents. And but then we ask that, okay, so this is the case in RD. Can we maybe do something interesting over not necessarily real spaces, but over any spaces? So this question of looking at incidences between points and hyperplanes, you can define this over any space. So what we ask that, given some field f, which can be a finite field, real field, whatever you want, and we have endpoints in this d-dimensional space and the set of n hyperplanes, then what is the maximum number of incidences between these if we assume that the graph is KTT-free? And for that, we managed to prove a bound which is very, very close to this upper bound of Applebaum and Scherrer. So we proved that no matter what field we look at, we get a bound independent of the field, which is just n to the 2 minus the ceiling of 2 over d plus 1. So again, just to compare with the bound of Applebaum and Scherrer, we get almost the same, but without the ceiling. So in particular, when d is an odd integer, then these two bounds are coincide. And why this was very surprising for us at first is that the proof of Applebaum and Scherrer, and actually all these previous geometric results about this.
So probably your ceiling, right? So you need to take d plus 1 over 2, and then, right, because this number is less than 1. If you are rounded to ceiling, it would be 1. I'm just saying some typo on the slide if you use it again.
Okay, it might be.
Right, so the ceiling of d over 2 over d plus 1 is 1. Just you need to first divide by this number and then take, right?
Yeah. Sorry.
Yeah, just to say to everybody, right? It's d plus 1 over 2, right? And then
sorry. Yes.
Then you take ceiling and then
So yeah, this should be 1 over. Yeah, this makes no sense, of course.
d plus 1 over 2.
Yeah, this is the bound we get. Yes.
Yeah.
Yeah, thank you. Yeah, sorry. Yeah, of course. So yes, so when d is odd, then now these two bounds are indeed the same. And so again, why this is surprising is that all the previous results, they use some highly geometric techniques like space cutting, space partitioning, the polynomial partitioning. So these kind of techniques which have absolutely no analogs over, say, finite fields. But we get this theorem by almost purely combinatorial techniques. And beyond that, our theorem is also sharp. So it is sharp in the sense that for every n and d, I can find the field Fdn, and in this d-dimensional space, a set of endpoints and then hyperplanes which achieves this bound. So this basically tells us that without any further assumption on the field, we cannot get a better bound than this. Yes. And so to give you some proofs, let me show you how to get this bound in the case d equals 3. So in the case d equals 3, we want to show the bound n to the 3/2. And so the main geometric observation, so basically the only geometric observation we need about these incidence graphs is that they avoid the following simple bipartite graph as an induced subgraph. So if we have a point plane incidence graph in F3, they do not contain this P3, where this P3 is almost the complete bipartite graph on vertex classes 3 plus 3, except we remove the very last edge. So there is no edge between the two last vertices. And this is basically all the geometric information we need. After that, we prove the following graph theoretical result, which says that if we have a bipartite graph with some vertices and no induced copy of P3 and no KTT, then the number of edges of G is at most constant t times n to the 3/2. Now note that after you prove this lemma, you are essentially done in the case d equals 3. And so let me prove this lemma for you. So the proof is as follows. So we have, so let's say we have a graph EG which has some large constant times 3/2 edges. Now we want to show that we either have KTT in G or we either have this P3. So let me just draw it again for you. So this P3, or either we have this in G as an induced subgraph. And now in order to show this, we will use the dependent random choice method, which is a So it's a very popular technique with probably hundreds of applications in extremal combinatorics, and this just shows the power of this, that it is also highly applicable for these Zarankiewicz type problems. So the idea of the proof is as follows. So let's say we have G. So here are the two vertex classes of G. So now we are only interested in the bipartite setting. And now what we will do, we will try to embed P3. And first we try to embed, let's say, these two vertices. And what we do is we just simply take two random vertices in A. And I try to embed P3 where these two vertices correspond to the first two vertices in P3. So what we do is we pick two vertices randomly from all pairs of vertices from the uniform distribution. And then first what we do is we look at the common neighborhood of these two vertices. So this is denoted by NUV. And then first of all, we want this neighborhood to be large so that we can find the bottom vertices of P3 or even some other structure. And so we can estimate the expectation of this, the size of NUV fairly easily. So what we can do is we just look at a vertex in X and we look at what's the probability that this vertex X has fallen into this common neighborhood. And now this vertex X is in the common neighborhood if and only if we pick two vertices from the neighborhood of X. So this is exactly just the size of the neighborhood of X. Choose 2 divided by and choose 2. So this is essentially just the sum of nx squared divided by n squared. And you can show using convexity or Jensen's inequality that this will be some large constant. So you can show that this will be c squared at least. So okay, so now we know that when this constant c is large, then at least the expected size of this common neighborhood is large. But even beyond that, this expected neighborhood has some very surprising properties. And one very powerful property of this neighborhood is that for all pairs of vertices, we expect to see a lot of common neighbors for those two vertices as well. And so now let me just tell you a bit more our strategy. So basically what we want, so first of all, we want that the size of the common neighborhood is at least t, and then we want to find two vertices in the common neighborhood such that their common neighborhood, which lives somewhere here. So let's say these are some x and y. Sorry for this picture. So we want that the common neighborhood of n xy is at least t as well. Because if we can achieve this, so if we get that the common neighborhood is at least t, then we either have two cases. So either every edge between nuv and then xy is present, in which case we get a complete ktt, or if there is an edge missing, then that missing edge together with uv and xy is actually a copy of P3. So maybe, so if there is a missing edge between this neighborhood and xy and then uv, which I now denote by this red edge, then these two vertices together with these four vertices, they will form a copy of P3. So we are done again. So now all that comes down to is to find actually two vertices xy in this neighborhood, which has a large common neighborhood. And in order to show this, we will we can show something even much stronger. We can show that basically all pairs of vertices in an UV, almost all pairs will have this property. So now say that a pair, let's say that xy is bad if x and y are contained in the neighborhood of UV and the common neighborhood, and xy is less than t. And then we can just calculate the expected number of bad pairs. So the expected number of bad pairs. Again, we just look for all pairs xy. But now we only have to look at those pairs xy where the neighborhood is at most t. So in this case, this is the, again, was the probability that x and y falls into the neighborhood of u and v. So this is just by the same calculation is the size of an xy, choose 2 divided by n choose 2. Now, but because the a pair is bad, if it is common neighborhood size at most t, we get that this is at most the sum roughly t squared over n squared. And even if we sum over all possible pairs, so not just bad pairs, but all possible pairs, we get that this is at most, say, t squared. So now if you compare the size of the expected size of an UV and the expected number of bad pairs in the neighborhood, now if you choose C sufficiently large, of course, the expected size will be much larger than the expected number of bad pairs. So just by a simple alteration method, you will find that not only there exists at least one good pair in the common neighborhood if UV with positive probability, but most of the pairs will be good. And also at the same time, the size of the common neighborhood will be large enough. And this is the idea of the proof. And so this was the D=3 case. So let me just give you a very brief overview in what to do when D is larger than 3. So the idea is similar, but things will become more complicated. So again, we will use the geometric nature of the construction of the point hyperplane incidences in MD to find the forbidden subgraph, and we find that the following kind of pattern PD will be forbidden. So now let me tell you what you see in this picture. So here this bipartite graph has vertex classes of size D, and where you see a normal black edge, it means an edge. Where you see this dashed red edge, it means that that pair is forbidden to be connected by an edge. However, there are pairs where we don't assume anything, so that there is no black or red edge, they can be either connected by an edge or not. So this gives a finite family of bipartite graphs, and we can show that just by simple combinatorial arguments that these graphs are forbidden in this kind of graphs. So after that, this is all the geometric information needed, and our proof becomes a graph theoretic proof. So what we show that if we have a bipartite graph with n plus n vertices, and we have no induced copy of PD and no complete bipartite graph KTT, then the maximum number of edges is exactly this n to the 2 minus 1 over, again, this is the bad exponent. So we get n to the 2 minus 1 over the ceiling of d plus 1 over 2. And this is the idea of the proof. And so maybe let me just finish this talk with some few results about what we do if we have more complex algebraic graphs. So similarly as in this geometric setting where we looked at graphs defined by polynomial inequalities in real finite spaces, we can look at what happens with graphs algebraically defined over some arbitrary spaces. So in particular, I will show you a result about incidences of points and certain varieties. So let's assume that we have a set of n points and a set of n varieties in f to the d, where f is again some arbitrary field. And we assume that each variety is of dimension d and degree at most delta. Now again, under the assumption that the incidence graph is KTT-free, we can show that the maximum number of incidences between these points and varieties is at most n to the 2 minus 1 over d plus 1. And this result is the best possible. So what does this theorem actually mean? So without going into too much algebraic geometry, you can just imagine a variety as the zero set and polynomial, and so if the dimension is kind of the complexity measure of this variety. For example, you can view a sphere as a variety which is the zero set of a 2-degree polynomial in R3, and then the sphere itself is a 2-dimensional surface, so the dimension is there too. Now you can define this kind of notion of dimension in an abstract setting without having to rely on this geometric intuition, which I will not do now. And you can also define the degree of the varieties, where this is the degree of this kind of defining polynomials. So zero set is very roughly. And so if we have this algebraic geometric setting, we also have a very good understanding of what the maximal number of incidences should be. And the proof idea is very similar to the proof of the point plane question. So we find some forbidden bipartite graph H d delta, which now will have the property that every degree in one of the sides will be at most d plus 1. And after we can define this bipartite graph, then we can just apply our results that I mentioned in the beginning of this talk, where we already know what the Zarankiewicz function of these kind of families that avoid these graphs. And here actually the hard part is to find this bipartite graph HD delta. So this will be some exponentially large graph with respect to the parameters, but this can be constructed. Yes, and this is actually all I wanted to talk about. So thanks everyone for your attention, and let me know if you have any questions.
Thank you, Istvan, for the interesting talk. So yes, please unmute yourself if you have questions to Istvan. Maybe I have, let me start with a question. So in real case, right, so for appropriate parity of D, right, so this result gives something which is equivalent to the best bounds which were known through other technique. So do you think there is some way to maybe combine these techniques maybe with this forbidding to try to improve? Because it seems that this indicates that in real case the result should be improved, right? So because you really, right, so this proof shows that you're really not using enough geometry, maybe showing that you're really not using enough geometry of the real space.
Yes, so in the real case, how the result is proved is also you have some graph theoretic lemma combined with combinatorial, with the geometric technique. And then you would expect that if you can improve this combinatorial part, then you might be able to improve this geometric part. However, we can do this, and we actually check what we get, but it seems like our improvement only kind of recovers the original bound if we boost this with these geometric techniques. So these exponents seem to be a genuine barrier to kind of any of these techniques.
More questions? So maybe one more question. So also in terms of finite fields, right? So this result is tight, but in finite fields, sometimes people improve the bounds by looking on like certain specific, right? So type of sets, right? The sets which are not very large. So you might say if I have not many points and not many lines, right? The size of the sets are somehow more controlled. Then maybe the answer is different. So what, right? So if I take over ZP, say, not very many lines and not very many planes and not very many points. So what you think would be?
Yes, so there is this famous result of good cats and tau, which shows that if you are in a if you're in 2 dimensions over a finite field and you have some control over the points and lines, then you can have an improvement. So in 2 dimensions, you would get n to the 3/2 points and lines if you just take all points and all lines. That gives n to the 3/2. But if you are somewhat below, so you ensure that you are not taking all points and all lines, then you can get a significant improvement in the exponent. So the proof of that is pretty hard, and there does not seem to be any generalizations for higher dimensions. So, but again, you would expect a similar phenomenon. So our construction, which achieves sharpness, it really can be realized for certain pairs of parameters. So if our parameters are a bit differ from this, then we expect the answer to be different as well. But currently, these seem to be beyond our techniques.
So actually, there is one result in higher dimension along these lines. There is this theorem of Rudnev, which shows you that you can improve the bound between points and planes in FP if you know that you don't have many planes, say less than, say, p-square planes in FP to the cube.
Oh yeah, so there is this one in, but it's only in R3s, and it also doesn't generalize.
More questions? If not, let's thank speaker again. Right. Thank you very much all for coming. And thank you, Istvan, for the very interesting talk. And we continue, we can stop recording.